This lesson is 4.5. This is graphing other trigonometric functions. So far we've learned about graphing sine and cosine. So we're going to talk about graphing our other trig functions. So in the last lesson in 4.4 we talked about translation and transformation rules for sinusoids, so for sine and cosine. And those rules were that the graphs of y equals a sine of bx plus c quantity plus d, or y equals a times cosine quantity bx plus c, that whole thing, plus d, and where a is not 0, b is not 0, obviously, so that we actually have a sine and a cosine, that the following is true, that our amplitude is equal to that magnitude of a, that absolute value of a, that our period is equal to 2 pi, because that is our period of sine and cosine, over our magnitude of b. Frequency is just 1 over the period, so you could also write that as the reciprocal. We could write it as frequency equals magnitude of b over 2 pi. Phase shift, so how much it's moving left or right, is affected by both c and b. So if we just have a c, then that is our phase shift. But if we have something in front of that x, then that is causing our function to go faster or slower, so that also affects our phase shift. So we call that our phase shift is negative c over magnitude of b. And the reason it's negative is because in all the rules we've seen before, we're moving opposite to whichever way we go. So when we had, for example, x squared as our parent function, and we had a transformation of x minus 2 squared, well, actually you're moving 2 to the right for that example. So that's why that one's negative. So it's negative c over absolute value of b. That gives you your phase shift. The negative c should be obvious for that phase shift. The absolute value of b that it affects is also pretty helpful because you know that that's affecting how quickly you're moving. The vertical shift, how much we're moving up or down, this works the same way that we know from our x squared, our quadratics. Our vertical shift is just that number at the end. Y equals this whole thing plus a number. So that plus a number is going to affect where you are on y at the end. And our midline, where we are, our cosine graph looks something like this. Generally our midline is at 0. If we add some number at the end, that means that we're moving that whole thing up. Our midline is going to be whatever we're moving up. So if we have a plus 0, our midline is 0. If we have a plus 1, well, our new midline is going to be 1. So the other 4 trig functions have similar rules, but it is important to remember that because they are essentially fractions, I should just say fractions, sorry, that they are rational functions. So we've seen rational functions before. We have some f of x over some g of x, right? In this case we have, for example, a y over x, right? Or we have, that's like tangent. And so for our other trig functions, all of them are fractions, right? Tangent is y over x, for example. Cotangent is x over y. We can go on and on and on. But we know that the other ones are the reciprocals of our original, so we have 1 over x, 1 over y, etc. So when we have rational functions, we know we have asymptotes whenever the denominator is equal to 0. So this is the difference of these 4 trig functions compared to the first 2. In the first 2, sine and cosine, we don't have any asymptotes. They're just periodic functions. They continue, no problems. Well, for tangent, cotangent, cosecant, and secant, we have asymptotes because we have a denominator, so we have an opportunity for that denominator to equal 0. So for tangent, the places where we're going to have a 0 is where what is tangent equal to? Y over x. So it's where x is going to equal 0. So if you were to look at where x equals 0, or even where the function cosine equals 0, those are going to cause asymptotes. So we can see here we have it at pi over 2, 3 pi over 2. And if you look on your unit circle, that is where x, the x-coordinate, is equal to 0. That is going to cause an asymptote for tangent. Transversely, where we are going to have zeros for tangent, where our actual function of tangent is going to equal 0, is where our y is going to equal 0. So where sine equals 0, or where on our unit circle our actual y-coordinate equals 0. So we are going to have zeros here at 0, at pi, and everywhere beyond that. Now it may not be obvious from this picture, but there's something else we know about tangent, which is where tangent is equal to 1. Now, we want y and x to be the same. The place that happens is at every 45 degrees. That's where we have tangent and, where we have y and x the same. So when we are at pi over 4, for example, we get a value of 1 for our tangent. And the way we can think about tangent is that we have a y over x, right? Where have we seen y over x before? Rise over run is sort of what that means. So as we move on this unit circle, we're talking about our slope. Our slope is getting higher and higher and higher and higher and higher and higher until it's undefined at 90 degrees, right? And then we're super high, super high, super high, but negative super high, super high, super high. And then we're getting lower and lower and lower and lower and lower until we're 0. So we're just talking about our slopes, and that's exactly what this matches. We're getting super, super high, super high, super high as we approach pi over 2, 90 degrees. And then right when we pass 90 degrees, we're super, super, super high, but really negative. And that's exactly what our tangent graph reflects. So if we look at cotangent, the exact opposite happens. So instead we're doing x over y. So we're basically graphing the reciprocal of this, and we have to think of it in the opposite way. So we have super high when we are at 0, and we have super low when we are at pi. Those are now our asymptotes whenever we had a y that was equal to 0 instead of an x that was equal to 0. If we graph cotangent and tangent together, you'll notice that the places where we had zeros for tangent, we have asymptotes for cotangent, and similarly, wherever we had zeros for cotangent, we have asymptotes for tangent. Let's move on to cosecant, and let's talk about sine, and then we'll talk about secant and cosine. So here are the graphs for sine that you know already, right? We go through 0. At pi over 2, we have a peak of 1. At pi, we have a 0. At 3 pi over 2, we have a negative 1. At 2 pi, we have a 0. That all matches our unit circle for our y values. That's what we're looking at on that unit circle. Well, what is cosecant equal to? Cosecant is equal to 1 over y. So the first thing that you might want to think about is, where is that function going to equal 1? Well, that's going to equal 1 where y equals 1, right? So at that value, we're going to have the same value for cosecant as we have for sine. If our y equals 1, our cosecant also equals 1. Similarly, if our y equals negative 1, that means our sine equals negative 1, and our cosecant equals negative 1. And that's exactly what happens. So at pi over 2, where we have a 1 for our sine right here, our cosecant also has a negative 1. And when we have a peak at this 3 pi over 2, we also have a peak at our cosecant. So we have a peak at our sine and our cosecant. We have the value negative 1 on both sides. But let's look at what happens at the zeros. So at 0, at the actual value of 0, we have a sine equal to 0, which means that we have 1 over 0. Well, we know that's going to cause an asymptote. So our cosecant jumps up into this infinity, right? Positive infinity, because we have an asymptote there. And at pi, we have another asymptote, so it jumps up there. We know we're going to have negative 1 at 3 pi over 2. We're going to have a similar curve causing that. So we have a curve from negative infinity up until negative 1 at 3 pi over 2, and then it goes down to negative infinity for 2 pi. So wherever we have a peak, we have a peak similarly for cosecant. Wherever we have a peak for sine, or a valley, you could say we have another peak. So our mins correspond to maxes, and our maxes correspond to mins. That works the exact same way in secant and for the same rules. You just have it shifted. So where we have a 1 at 0, so if we plug in 0 for our x for cosine, we get a value of 1. For that same thing, because secant is just equal to 1 over x, if we plugged in a 0 into that function, we would get a 1 because our x at the function 0 is equal to 1. So you have to look at what your value equals at that coordinate. So at that coordinate, we get an x value of 1. So again, we had a max on our cosine, we have a min on our secant. We have a min on our cosine at pi, we have a max at our secant. At pi over 2, we have zeros, so we have infinite discontinuities. I put a link to Desmos in here with some trig functions in there. You can play with those. You can adjust the values and see how adjusting one value adjusts the other one, and if we have a transformation of cosine, how that would affect secant, and so on. So I would recommend going in and playing with that and just getting familiar with how those things affect each other. Let's talk about damping. So when a trig function is multiplied by another trig function, the graph takes on the shape of the trig function constricted by the other function. So that sounds like a bunch of craziness, right? So what I'm saying is, if you have a cosine graph and you're multiplying that by something linear, the result in that graph is going to be something that looks like both cosine and something linear. It's going to take on both characteristics. So we call this damped oscillation. Oscillation, you know, we're going up and down, up and down, up and down. These are our cosine graphs or our sine graphs. And damped is that we are restricting that. So we have damped oscillation. The product of two functions is referred to as damped trigonometric function, written in the form y is equal to some f of x times cosine x, or some f of x times sine x, where f of x is, you guessed it, the damping factor. Damping, damping, damping. Okay, so in this one we see we have, does anyone know what this function is? You should be familiar by now. Sine of x. This is our graph sine of x. I've pulled it out pretty far. And we have some linear function 2x. So our f of x is equal to 2x. And we want to know what y equals 2x times sine of x looks like. So what's going to happen is it's going to fill, if you notice where we have zeros or where we have peaks, zeros, peaks, zeros, peaks, and if we were to draw a negative 2x in order to fill the other side, what's going to happen is our sine graph is going to take that peak all the way up until that 2x. It's going to leave the 0 where the 0 is, and it's going to bring the other peak, our negative, our minimum, down to that negative 2x. Our maximum is going to rise up to that positive 2x. Our minimum is going to go down to that negative 2x. So it's going to oscillate like this. And I'll show you a graph that looks less like childish drawings, which looks like this, and it's exactly what it does. So this graph is the graph of 2x times sine of x. I have another Desmos graph set up. If you want to go to that link and play around with some more damping, you're welcome to.